Good morning. In this lecture, we are going to see fluid dynamics. Fluid dynamics is the study of fluid motion by considering the forces causing the motion. When a fluid is in motion, various forces will act on the fluid. The various forces are force due to weight of the fluid, that is gravity force, force due to fluid pressure, that is pressure force, and force due to viscosity, viscous force, and force due to random motion of the fluid, that is turbulence, and force due to compressibility of the fluid, that is variation in density. So these are the different forces acting on the fluid when it is in motion. So we cannot consider all forces at a time and derive the equation of motion. We can consider either 2 or 3 forces and we can neglect the effects of other forces and we can derive the equation of motion. So first of all, from the Newton's second law of motion, we know what is equation of motion. The force acting on a fluid is equals to mass into acceleration, or we can say other words, the force acting in a particular direction equals to mass into acceleration in that direction. Now we are going to consider only the two forces acting on the fluid, those are pressure force and gravity force, and we are going to derive the equation of motion, that is known as Euler's equation of motion. By considering only pressure forces and gravity forces acting on the fluid element, we are going to derive the equation of motion. F equals to ma. F is the net force acting along a particular direction, m is the mass of the fluid, and a is the acceleration of the fluid. So for this we are considering flow along a streamline. Consider this is the flow along a streamline. S represents streamline, and consider a small cylindrical element for our analysis, which is inclined some angle theta to the weight of the fluid. Now we can observe the various forces acting on the fluid element. Here fluid is entering and here it is leaving along the streamline. At the inlet we have pressure force P times dA. dA represents small elemental area. Since we have considered a small elemental volume, this is the pressure force at the inlet. Similarly, this is the pressure force at the exit. The pressure may vary along the streamline. It may increase or decrease. According to Taylor series, we are writing pressure at some S plus delta S equals to pressure at S plus rate of change of pressure along that direction for a length of ds. The element is having a length of ds. So here the pressure will be pressure at this point plus rate of change of pressure with respect to S for a length of ds. Now this is the pressure at the exit. And one more force acting is the force due to gravity or weight. This is mass into G. M we can write as density into volume. Again volume can be written as dA into ds. Area into length is the volume. Rho is the density. Rho Vg is the weight of the fluid acting downward. So now these are the forces we are considering. Only forces due to pressure at the inlet and exit and force due to gravity. And we are deriving the equation of motion along the streamline. So now we can write the net force acting on the fluid element in the direction of S equals to mass into acceleration of the fluid in the direction of S. So the net force acting is, this is the force due to pressure at the inlet, this is the force due to pressure at the exit, this is the component of weight along the streamline direction. This is having two components. One is cos component along the streamline direction and one is sin component along the normal direction to the streamline. So we have considered the cos component along the streamline. Now this is the net force acting on the fluid element. So according to Newton's second law, net force acting along any direction equals to mass into acceleration in that direction. So now we have to find mass and acceleration. Mass is nothing but density into volume. Again, volume can be written as dA into ds. So mass already we know. Then we need to find the acceleration along the streamline direction. So acceleration equals to rate of change of velocity with respect to time. Acceleration equals to dv by dt. But velocity may vary along the streamline and with respect to time also. So velocity is a function of both space along the streamline and with respect to time also. So now we can write dv by dt. We have to apply partial differential. Since velocity is function of both space and time, dou v by dou s into first with respect to first variable and second with respect to second variable. Dou v by dou s into again ds by dt. This one also similar, dou v by dou t into dou dt by dt. Since this is same, so we will get this one, dou v by dou s into ds by dt. Again this one ds by dt is rate of change of displacement with respect to time. This is known as velocity. Again we can replace this one as v. So we will get finally acceleration equals to v times dou v by dou s plus dou v by dou t. So we know from the Newton's second law, net force acting equals to mass into acceleration. This is the mass of the element. We have already discussed density into volume. Now this is the net force acting. The first term represents force due to pressure. The second term represents force due to weight or gravity. This one represents mass. This one represents acceleration. Net force equals to mass into acceleration. So dA and ds is same on both sides. By cancelling dA and ds, we will get this one. And the fluid element is inclined at an angle of theta to the vertical. We have taken ds as the length of the fluid element. dz is the vertical difference in datum or difference in datum at the inlet to the exit. So we can write cos theta equals to dz by ds. dz is the difference in datum level of the fluid element from inlet to exit. We can replace cos theta by dz by ds in the above equation. In place of cos theta, dz by ds. Now for making it further simple, we are taking the assumption of steady flow. Steady flow means the dynamic properties of fluid or hydrodynamic properties of fluid does not vary with respect to time. So they are function of space only. So velocity will not vary with respect to time. At the same time, other dynamic properties like pressure, density, etc. will not vary with respect to time. So velocity is function of space only. Pressure also function of space only. So here we can cancel this term since it is a steady flow. And one more thing is here it is partial differential. Now we can replace this partial differential with ordinary differential. Since here we have taken the assumption the properties are not function of time. So pressure is function of space only, one variable. We can replace partial with ordinary differential. Similarly, here also dou v by dou s we can write as dv by ds since velocity is function of space only. Now we can further simplify this equation by bringing these two terms this side and equating it to 0 and taking rho as the common. We can finally write this one as this one, and again we can write this one as since ds, so this should be ds. So ds is common, we can write this one as finally this one dp by rho plus g dz plus v dv equals to 0. This is known as Euler's equation of motion. We have considered only pressure forces and gravity forces while deriving the Euler's equation of motion. Now by integrating this equation we can get the Bernoulli's equation. Integral dp by rho plus integral g dz plus integral v dv equals to integral 0. For integral 0 means it's constant. So for making it further simplify, we are taking the assumption of the flow is incompressible. Incompressible means density will not vary along the flow. So we can take density term outside the integration. that one become 1 by rho integral dp plus g. Anyway, g is constant acceleration due to gravity. G times integral dz plus integral v dv. By integrating it, we will get p by rho plus gz plus v square by 2 equals to constant. The same expression can be written as p by rho g plus v square by 2g plus z equals to constant. This is known as Bernoulli's equation. This implies the first term implies p by rho g. This indicates pressure energy per unit weight of the fluid. Second term indicates kinetic energy per unit weight of the fluid. Third term indicates potential energy per unit weight of the fluid. So we can state the Bernoulli's equation as this one is pressure energy, this one is kinetic energy, and this one is potential energy. Sum of kinetic energy, pressure energy, and potential energy at any point in a flow is same. So while deriving the Bernoulli's equation, we have taken certain assumptions. The first assumption is we haven't considered the viscous forces. So that means indirectly the fluid is ideal fluid, no viscosity for that fluid, since we haven't considered the effects of viscosity. The second assumption is the flow is steady. We have taken dou v by dou t equals to 0 in the middle of the derivation. With respect to time, the properties are not varying. The third assumption is flow is incompressible. Variation of density along the flow is negligible. And the fourth assumption is the flow is irrotational. These are the four assumptions we have taken while deriving the Bernoulli's equation. This is the statement of the Bernoulli's equation. It states that in a steady ideal flow of an incompressible fluid, the total energy at any point of the fluid is constant. Total energy means sum of pressure energy, kinetic energy, and potential energy. This is the derivation for Bernoulli's equation. This one we got by integrating the Euler's equation of motion. Now we will solve one problem on the Bernoulli's equation. This is the problem. In the problem, a pipe of diameter 400 mm carries water at a velocity of 25 meter per second. The pressure at points A and B are given as 29.43 Newton per centimeter square and 22.563 Newton per centimeter square, while the datum head at A and B are 28 meters and 30 meters. Find the loss of head between A and B. So the pressures at point 1 and point 2 are given. Diameter of the pipe is given. Velocity is given. And then datum is given. Since pipe diameter is constant, it's not varying. So velocity at point 1 and point 2 will be same. So we can consider only pressure forces and force due to datum. This is the first point, which is at a height of 28 meters from the datum line, and this is the second point, which is at a height of 30 meters from the datum line. We know pressure at point 1 and pressure at point 2, and velocity will be remain same since pipe diameter is not changing. From the continuity equation, a1 v1 equals to a2 v2. If the cross sectional area is constant, velocity will not vary. So v1 equals to v2 equals to 25 meter per second. Pressure is given in Newton per centimeter square. We have to convert it into Newton per meter square. Every unit should be in SI units only. So finally what we have to find is we have to find the loss of head between A and B. While deriving the Bernoulli's equation, we have taken the assumption that the flow is ideal. But in general, if we apply the Bernoulli's equation for a real fluid, suppose fluid is flowing from here to here, the energy will decrease since due to some losses, the energy at point 2 will be less than energy at point 1. So if we find the total energy at point 1 and if we subtract total energy from point 2, then we will get the losses. So the total energy at A is P by rho g plus V square by 2g plus z. And total energy at B is same, P by rho g plus Vb square by 2g plus z. This is the total energy at point A and this is the total energy at point B. If we subtract this one from this one, we will get loss of energy in meters of water column. 5 meters is the loss of energy. So Bernoulli's equation can be applied only for the ideal fluid. For real fluid, on the right hand side we will get one term, that is the extra term, loss of head. So the next problem is regarding the pipe bends. Pipe bends is the application of momentum equation. The momentum equation states that the net force acting in any direction equals to change of momentum per unit time. By applying that principle, we have to solve the second problem. It is given that the pipe bend angle is 45 degrees and diameters at inlet and outlet are 600 mm and 300 mm respectively, and we need to find the force exerted by water on the bend. Intensity of pressure at inlet is given and volumetric flow rate is given. So first we have to write the given data. The given data is angle of the bend, diameter at inlet and diameter at outlet. So the next thing is corresponding to that the given bend angle, we have to draw the pipe bend. We have to represent the various forces acting on the pipe bend. So the first thing is, according to the 45 degrees angle, we have to draw the pipe bend. It is mentioned that it's a reducing pipe bend. So means the diameter at the inlet is more than diameter at the exit. So next thing is, we have to represent the various forces acting on the pipe bend. Fluid with a velocity v1 is entering into the pipe bend. While entering, it will exert some pressure force on the fluid element inside the bend. That pressure force is P1A1, pressure at inlet into cross sectional area at the inlet. Similarly, here the pressure force will be in this direction, P2A2, the pressure force exerted on the fluid in the bend, P2A2. Now we can resolve this into two components, along x direction and along y direction. This one will become cos component and this one will become sin component. The fluid is living with a velocity v2. Again we can resolve this one into two components, cos component and then sin component. And other forces acting are Fx is the force acting on the bend by the fluid along x direction, and Fy is the force acting on the bend by the fluid along y direction. Now we are considering only the forces acting on the fluid element in the bend, but Fx is the force acting on the bend. So according to Newton's third law, the bend also will exert the same force on the fluid in opposite direction. So minus Fx is the force acting on the fluid by the bend in x direction. Similarly, minus Fy is the force acting on the fluid by the bend in y direction. So now we are considering only the forces acting on the fluid element. So these are the forces acting on the fluid element: pressure force at the inlet, pressure force at the exit, and minus Fx and minus Fy. Now we can write the net force acting along x direction and again net force acting along y direction. From the momentum principle, net force acting along any direction equals to rho into density into discharge, volumetric discharge into final velocity in that direction minus initial velocity in that direction. Now we can apply the same principle along x direction and y direction. Net force acting along x direction equals to, this is the pressure force along x direction at the inlet, and this is the component of pressure force along x direction at the exit. So this one should be minus, this one is positive since we have taken this direction as the positive, and one more force is minus Fx. This is the net force acting along x direction, and according to momentum principle, that is equals to rho into q into v final minus v initial along that direction. Along x direction, the final velocity is v2 cos 45 and the initial velocity is v1. So final velocity minus initial velocity. From this we can find Fx equals to, take Fx this side and this term this side, we will write finally Fx, the force acting on the bend by the fluid along x direction, is this one. Similarly, we can write along y direction also, the net force acting along y direction is At the inlet we have no component along y direction. At the exit this is the component of pressure force along y direction, and here this is the reaction force offered by the bend on the fluid along y direction. So only these forces constitute the net force along the y direction, that is equals to rho into q into final velocity along y direction is, this is the final velocity along y direction, and initial velocity along x direction is 0 since the fluid is entering horizontally. Thus constitutes the momentum equation along y direction, this one. From this we can write Fy equals to minus P2A2 sin 45 minus this term. So now for finding the resultant force we need to find Fx and Fy. For finding Fx we need to know P1. P1 is given, A1 is given, P2 we don't know, A2 is given, and rho density we know for water 1000 kg per meter cube, and Q volumetric flow rate is given, and V2 we can find, and V1 is given. So only thing we need to find is the P2. P2 can be found by using the Bernoulli equation between point 1 and point 2, or at the inlet and exit we can apply the Bernoulli equation and we can find the pressure at point 2. So this is the P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g plus V2 square by 2g plus Z2. Since point 1 and point 2 are almost at the same level, not exactly, but we can make a valid assumption that Z1 equals to Z2, and finally it will become P1 by rho g plus V1 square by 2g equals to P2 by rho g plus V2 square by 2g. V1 is given in the problem, discharge is given and diameters are given. We know from the continuity equation Q equals to A1 V1 equals to A2 V2. By using this one we can find the velocity of the fluid at the inlet of the bend. Similarly we can find the velocity of the fluid at the exit of the bend by substituting this one in the Bernoulli equation. We know all the things exit, pressure at the exit. So we can find the P2. P2 value is 5.45 into 10 power 4 Newton per meter square. So now we can substitute all the values to find the Fx and Fy. So after getting Fx and Fy, this is Fx 19911.4 Newton and this is Fy. Fy we got negative, that indicates that direction we have taken is the wrong, we have to reverse the direction. Fy we have taken upward, the force acting on the bend by the fluid, so we have to take now downward, and Fx is this side, this is the resultant force acting on the bend. The direction we have to find by using tan theta equals to Fy by Fx. From that theta equals to tan inverse Fy by Fx. Here theta is the angle made by the resultant with the Fx. Thank you.